Hello students, in the last videos so far in our discussion of laws of motion we discussed the three laws of motion and they are called as Newton's laws of motion, otherwise called as Newton's laws of motion, and already we know the statements of the three laws. And the first law, it says or it gives, if no external force acts on a body, the body will continue in the state of rest or maybe in the rest or in the motion. And the second one is the when a force applied on a body, then that force is proportional to the rate of change of linear momentum, isn't it? So that we discuss in the second. And in the third one, to every action there is an equal and opposite reaction. So my point is to recall the three laws. Today's video is for, we can say that out of these three laws, yes, Newton provided us the three laws of motion, and we got the three laws. By using these three laws in classical mechanics, we deal with so many, or we got the solutions of so many questions or problems like that. But as a whole, as we are in the modern society, so as a whole, we can say yes, Newton has provided given three laws, but we can say that the second law is actually the real law of motion. So in this video, we show that, we prove that actually the Newton's second law is the real law of motion. So that's why it is written that I will prove here the Newton's second law is the real law of motion. It means what? The real law means if Newton will give us, or if the Newton's not like that. So if Newton's second law is known to us, then we can derive or we can find first law, and also we can find the third law. That's why it is called the second law is the real law of motion. So means what we will come across here to prove this, if I will prove anyway, the first law is there in the second law and the third law is also in the second law. Then I can say it is the real law of motion. Okay. So now first I will go for the first step. First law is contained in the second law. First proof. First law is contained in the second law. In the second law. So means we know the second law. The second law is the rate of change of linear momentum is proportional to the applied or external force. We know that, and we have to prove that if no external force acts on a body, it will continue its state of rest or uniform motion. That we have to prove here. So now to prove this one, as you know the second law, so I will first write according to Newton's second law. According to Newton's second law. According to Newton's second law, what we know that the applied force F or F equal to mass into acceleration. This is the case where m is a constant. We have taken always the m is a constant in our classical concept. In our classical concept, we will always consider m is constant. So according to Newton's second law, if a body of mass m moving with an acceleration a, then the force acting on the body must be m into a, provided m is equal to constant. From here, as this case, if I will consider that the applied force, there is no applied force, means if no external force applied on the body, then this magnitude of the force F is equal to 0. I have considered the magnitude part. You can take also direction by putting the direction like F and A. So the external force you can take as a 0. So if no external force applied on the body, then F is equal to 0. So if F is equal to 0, it means we have, if F is equal to 0, then putting that here, your MA should be equal to 0. But it is the multiplication of two quantities, mass and acceleration, that is equal to 0, but mass is never equal to 0. If a body exists, it has mass cannot be 0. Because in classical concept, we are discussing the Newton's era, we are discussing about the Newton's law. So here, we always consider mass is constant. So, but mass is never 0, because the body has existence. If mass is not equal to 0, then acceleration is equal to 0. What it means acceleration is 0? Means the body is not accelerating. From equations of kinematics, if I go in detail, from equation of kinematics, what we know? If a body has a final velocity v and having an initial velocity u, moving with an acceleration a, and the time taken to change the velocity u to v, the relation is v is equal to u plus at. But in this concept, if a is equal to 0, then put a is equal to 0, v is equal to u, final is equal to initial. That is the proof. V is the final, u is the initial. So in this concept, if the body is at rest, means if the body is at rest, let me write here, if the body is at rest, then u is equal to 0. Put u is equal to 0. Then body at rest, initially 0, then v is also 0, provided acceleration is 0. We have proved that acceleration is 0 if no external force acts on the body. Then if it is moving with a velocity u, then the velocity will continue, u is equal to v, e is equal to v. So initially equal to final, there is no change in velocity. So the acceleration is 0. In that way, what we conclude? No external force applied, so long as no applied force acts on a body, it will continue in the state of rest, will remain at rest. Or if it is moving with a velocity, it will remain in that velocity, in the same velocity. This is the Newton's first law of motion. So the first law is contained in the second law. Clear? In that way, we will go for the second part. Second part is that I will prove here the third law is contained in the second law. Then my point is clear. The third law. So third law is contained in the second law. Second part is the third law, means Newton's third law. Third law is contained in the second law. To the same procedure here, sir, we will consider an isolated system. Consider an isolated system of two bodies A and B. Remember, student, generally we will come across these words isolated. What it means isolated? Now, if I say an example like you are isolated from the college. Clear? Because there is no impact of college when you are in your house. Isolated in the sense that there is no external force acts on the system. Now the question comes here, what is a system? If this is a system, yes, this is a system. If the hand holding this is also a system. And the room is also a system. The universe is also a system. So system means that is in your mind. Up to what particles, up to what I will consider that is a system. So these two things you should remember. Isolated means there is no external force acts on the system. That is called as an isolated. So a body is isolated means the body of its own. It is no interaction with the others, or there is no interaction of others with that body. Interaction means that is your force. So in that case, when you are considering that for an isolated system of two bodies, so my system here, my system is for two bodies. You can say, as I already told, the system is up to the observer. If I say this room is a system, water coming under these particles, they are in the system. So in that way, there are two particles, right? A and B are the two bodies. A and B are the two bodies. And this is the system, right? So in this concept, now an isolated system, there is no external force acts on these two. Now let they have moving, or they are moving with some initial velocity. Suppose this is at u1 and this is suppose u2, moving along this path. Two bodies A and B moving like this. So at the interaction time, obviously u1 is greater than u2. Suppose the velocity of first one is greater than second. So the first one is moving on the same straight line. They are moving. The speed of A is greater than the speed of B. So it will interact. So during the interaction, what happens? Let me show you. A and suppose this is the B. A and B. Let this the mass is m1. Its mass is m. So during this interaction, what happens? They have some interaction. When they collide, there is some interaction. Means there is some interaction means yes, A can exert force on B and B also exert force on A. And that interaction is their internal. You are not applying any force during this interaction or after moving these two bodies. I am considering what happens before that, that is not a matter. As we already know that Newton's second law does not take the back what happens to the particle. Means before the change in momentum, if you apply a force, before that what is the state of the body or what is the acceleration, what is the body, that is not a matter. The Newton's second law, that's why it is the rate of change of that instant. At that instant what happens? Accordingly, so during this interaction, let force exerted on A by B, suppose FAB. Force on A by B, and this accordingly, then A exert force on B, so let that is your FBA, force on B by A. Don't say I have never used that one, they are equal or opposite like that. Already you know the third law, but I will prove here the third law from second law. So I don't know about these two. During the interaction, there must be a force exchange between them. There must be a force exchange between them. That I have considered. Clear? Now, on that basis, FAB is the force on A by B. Similarly, FBA is the force on B by A. That I have considered. And as M1 and M2 are the masses of the two bodies, yes, M1 and M2, this is the mass M1, it is the mass M2. Right? So M1 and M2 are the masses. Suppose a force is applied on a body A. From where the force comes, that is not a matter. If a force is applied on a body, then what happens? The rate of change of momentum, according to Newton's second law, that already you know that. So next, dPA or dP1 by dt or PA, suppose PA, dPA by dt is the, obviously this vector is the rate of change of momentum, rate of change of momentum of A. And this is from second law. If force on A is FAB, then this will change the momentum, and that is dPA by dt. Small change in momentum in a small time interval dt because of the applied force FAB. So, if this is the case, according to second law, according to Newton's second law, can I write this FAB is equal to dPA by dt? Individually, I am considering individually the force on A by B or whatever may be. That force on A will change the momentum of A. Similarly, let me make the same thing here. Okay, already written this one. I will not repeat again this thing. Similarly, if I will consider here, let check this what I am changing. dPB by dt is the rate of change of momentum of B. Why? Because force on B is also there. This is the force on B. So this is my first equation by considering the first case. In the second case, what I will write? If dPB by dt is the rate of change of momentum of B, according to Newton's second law, FBA is equal to dPB by dt. Equation 2. Clear? Got it? Now, adding equation 1 and 2. Adding equation 1 and 2. Adding equation 1 and 2. Adding equations 1 and 2. Now add these two. FAB plus FBA is equal to dPA by dt plus dPB by dt. And obviously these are vectors, right? This is the addition. Now, as we know, what is the second law? If there is no external force acts on the system, individually force acting on each particle, but as a whole in the system means the two body system A and B, is there any external force applied? No. If there is no external force acts on the system, applied on the system, then what is the rate of change of momentum of the system? So let me write the sentence that is most important. No external force, no external force. Why no external force? Isolated. No external force acts on the system, not on the particle A or B, on the system. No external force acts on the system. No external force acts on the system. So the change in momentum of the system means dPA, change in momentum, and dPB, change in momentum. A and B, that should be equal to 0. If no external force acts on the system, so change in momentum of the system is 0. Change in momentum of the system is 0. For the system, individually, first we gone for individually. For the system, no external force, for the system, there is no changing. Individually momentum changes because of individual forces on each particle. When you consider A and B as a system, then this is the case. If this is equal to 0, then from equation 3, that's the equation 3. From equation 3, FAB plus FBA is equal to 0. Because RHS is 0, so LHS is 0. Or I can write FAB, force on A by B, is equal to minus force on B by A. That is the Newton's third law, right? That is the Newton's third law. They are action and reaction, equal in magnitude, opposite in direction, right? Equal in magnitude and opposite in direction. So this is the third law is contained in the second law. To every action there is an equal and opposite reaction. So A gives an action to the B, so B obviously gives the reaction to A. That is the third law is contained in the second law. So last one we will write, hence both the third law and first law contained in the last sentence we will write both the third law and second law, third law and first law contained in the second law. So Newton's second law is the real law of motion. Okay. So after this proof of the second law is the real law, then we will go for another concept, or we can say this is applications of these Newton's laws to find the apparent weight of a person in a lift or elevator. So I can say that this is a problem type, this is a problem you can say also. Apparent weight, that means there must be a true weight and we are finding this apparent weight. So the weight may be true weight or a apparent weight, that we got a idea. That's why I have written this apparent weight, means there is a true weight and there is an apparent weight. So apparent weight of a person in a lift or elevator. So already you have an experience that a lift or elevator, inside the lift or elevator when you are standing, then there is you are getting a term that is called apparent weight. So what is this apparent weight? Now take a simple example that suppose this body is falling from a certain height, right? So this body falls, right? Why this body falls from a certain height? When I leave that for a free falling case, the body fall down. So the case is that when this is the body or a ball, then allowed to fall for a free falling case, this is the ground, the body fall down. Because of what? As you know, the weight that is equal to Fm is the mass and G is the acceleration due to gravity. Because of this weight, the body fall down. That is the common experience, already we know that. But when the body fall down like this, means a force is acting, the weight is nothing but the force, that is the force of gravity, force exerted by earth on the body, and the body falls down means the body tries to come towards the center of earth, not to the surface of earth. The body always tries or tends to come towards the center of earth, not the surface. So when the body fall down, now in between the path, suppose it comes down, when I keep here, now when the body hit here, so this is the surface of earth, the ground is the surface of earth, suppose, but in between if I put my hand, the body comes here. So what happens to the body? As the weight is acting on this body, right? Now the same case is that, suppose I will consider in the next part, when the body comes down, this is the surface and the body now comes here and comes to rest. Yes, what you observe? The body comes to rest. The same case is on the ground also or in between its path. When you leave, it will go to the surface. In between, suppose we will place that, it will comes to rest. What makes the body to rest? Means as the weight is never zero, because it is a mass, the same thing is happening here. Yes, earth is also attracting, because this is not the center of earth. The earth is like this, the center of earth is here. So the body will come to here, tries to come to here, but in between the body stops. So now question comes in your mind that what makes the body to stop? So you can say that because I hold here, so the body stops, but that is not the physics concept. Because you pick up this one, so the body stops. That any layman can say. But as a physics student, as a physics one, on physics point of view, I can say that, or you can also understand the thing is that there must be another force acting on this body, which balance this weight or this force. There must be another force acting on this body, and that force must be equal in magnitude of this one and opposite in direction. What that force is acting like this, and this must be equal in magnitude mg but opposite to direction, and this mg is called normal reaction R, or sometimes it is also taken as n. R or n, that is up to you, you can consider. Okay, so let me, my point of case, I will take R. So this is the normal reaction. So why I am going this concept? Because to know this apparent weight, we should know this concept. A book is lying on the table. The weight of the book is vertically downward, so the book should come down. The book should come down and it will goes to the center or will be attracted toward the center. But because of this table, now we cannot say that, because the table is there. On physics point of view, we will say that there is another force acting on this book which keep the book on the table, and that another force is equal to, if the book is not falling, is equal to the weight of the book, and that force is called normal reaction. So who applies this normal reaction? Earth gives this weight to this body, it is attracting this force. Who applies this normal reaction? The surface, where it rests, the surface applies the force. The surface gives the normal reaction. So why it is named so? So R is the normal reaction. Normal reaction. Now understand this more clearly. This is the table, surface. Suppose this is the book lying on this table. The weight is there, but the book is not coming under. Normal reaction is there. Who applies this normal reaction? The surface of the table applies the normal reaction. That is your R, which is equal to mg. So the body is at rest. The body is at rest. Now, the surface of the table applies the normal reaction. But in this case, there is no surface is there is no normal reaction. When it hit the ground, the normal reaction comes. Means, so long as the body is in air, there is no contact of the body with any other surface, the normal reaction is not there. That's why when we are discussing about the contact force, there I told that normal reaction is a contact force. In most of the time, this normal reaction comes when there is a contact between two surfaces. So it presses the surface, the body presses the surface, so the surface gives the normal reaction. And if this is the action, this is the reaction, so that's why it is called reaction. If this is the action, this will be the reaction. And why it is normal? Normal means perpendicular. It is always perpendicular to the surface where it places. On that surface where the body is placed, where it is in contact with the surface, to that surface it is normal. That's why it is called normal reaction. Okay? So after knowing this normal reaction, then we can understand this apparent weight. So again we will say that it is always like that. So in this case I have considered the surface is horizontal. If a surface is inclined, so suppose this is the earth and a body is placed here, inclined, then you can get a clear idea about this normal reaction. Again, you will get more clear idea about this normal reaction, because this is important to understand this apparent weight. That's why I am going in detail about this normal reaction. What is the weight of the body? Vertically downward. It is always toward the center, mg. Let me make like this, mg. Now, normal reaction X, the body is in contact with the surface. Suppose this inclination is theta. Now the body is on the surface like this. Now the surface is inclined here like this. How much angle it inclined? Theta. If the case, see here, what is this thing?
R mg. It will never change. Now this body surface, think this is the surface because this is the point of contact, rotates how much? Theta. So initially the R, what the R, that will also rotate like this. This is the R. Because it is always normal to the surface, this surface. So this should be 90. So the R will be like this. But mg is vertically downward. Very, very important. R should be like this. So this is the R. And this is the weight mg. R should be perpendicular to the surface. Right? So in this case what happens? Here you see R and mg are not equal and opposite. What happens here? If the surface is inclined, the body fall down. Fall down means the body will come here. Why? Because there are two component forms. If you go for the component forms, if this angle is theta, this will be theta. You can prove that. If theta, this is 90 minus theta. Then if 90 minus theta, then this angle is what? If this is 90 minus theta means this total is 90. It is 90 minus theta means this angle will be theta. The proof part is there. You can prove this one. So this is theta. So theta means this is mg cos theta, one component. Another rectangular component on the surface, mg sin theta. So this normal reaction now balance this mg cos theta. They are equal and opposite. They are equal and opposite. This mg sin theta, there is some resultant force acts on the body. This is another force. Because of the weight, the body slide. I have not considered about the friction. When you understand the friction, then you will go for the friction. So this is the normal reaction. And this normal reaction acts on the body. This normal reaction is the apparent weight of the body. This normal reaction is the apparent weight of the body. Clear? The normal reaction is the apparent weight of the body. I can say, remember one thing, what the apparent weight? The normal reaction on the body by the surface is the apparent weight of the body. And what the weight of the body, that is the true weight, or with what force the earth is attracting the body, that is the true weight. The normal reaction is the apparent weight. And in this concept, now we will go for the apparent weight of a person in a lift or elevator. So let us consider, there is the lift is there, and this is the floor of the lift, and a person is standing inside the lift. Okay, there is a person standing inside the lift. Now in this part, inside the lift, this is the floor of the lift. So the person is pressing the surface of the lift will give the normal reaction. The lift will give the normal reaction. So in this case, the person has a weight applied mg, and the lift will give a normal reaction R. And this R is the apparent weight, this is the true weight, and this is the apparent weight. I will go for one by one case 1. When the lift is at rest, when the lift is at rest, when the lift is at rest, what is the net force acting on this lift? 0. So the no force acting on this means mg should be equal to R. Mg should be equal to R. Clear? So when the elevator is at rest, no force is there, they cancel each other, mg and R, they cancel each other. So that is the first one. Means here what you can say, the apparent weight of the person is equal to true weight. True weight, this is the true weight, is equal to apparent weight. In the same case, when the lift moving with uniform velocity, when the lift is moving, when the lift is moving with uniform velocity upward or downward, vertically upward or downward. The elevator is suppose moving upward with a uniform velocity u or downward with a uniform velocity u. If the body is moving with a uniform, the lift as a whole system I will consider, this is moving with a uniform velocity, means the person inside the lift, it is also moving the same velocity. The person is also moving with the same velocity. So if both are in the same velocity, then for a uniform velocity, what is the acceleration? Acceleration is 0. So the second case is the lift is moving with a constant velocity, moving up, upward or downward, then acceleration is equal to 0. This happens when this happens, now all of you has an experience of lift, okay. When you are inside the lift, when the lift starts moving, going up suppose, upward, vertically upward, then initially what happens, the lift is at rest and you are inside the lift. First it changes its velocity, means from rest to it increases up to certain height, it increases velocity. Then it comes to constant velocity. It moves to a constant velocity. So suppose you are going from the ground floor to third floor. So before that third floor, again what happens? That velocity goes on decreasing. So here initially accelerating, then uniform acceleration, not uniform velocity, 0 acceleration, then deceleration, then comes to rest. That is the common experience. So in that basis, the acceleration is 0, means no force is acting, so F external is 0. Mass acceleration is 0 means the total system has a force is 0. So if this is 0, then obviously mg should be equal to r. Same case, true weight is equal to apparent weight. Okay, then so these two cases, when the lift is moving vertically upward or vertical downward, then mg is equal to r. Then go for the next one, the third one, case 3. When the lift is moving vertically upward with uniform acceleration, when the lift is moving vertically upward with uniform acceleration, the lift is moving like this, okay, with an uniform acceleration. So here what happens on the system, if a body is moving with an acceleration a, so I can say the person is also moving with an acceleration a along with the lift. So what is the force acting on this person? The force is, if m is the mass of the person, m is the mass, then m into a is the force on the person. Okay, m into a is the mass into acceleration, that is the force. So in this case, the resultant force F, understand this thing, resultant force F must be equal to, in what direction the resultant force? There are three forces. Because of mass there is an acceleration, this is the resultant force. This resultant force F is equal to, as mg, r is upward minus mg. Why I have considered this r minus mg? Because the resultant force F is equal to r minus mg, means there are two forces r and mg. Because of r, the body is moving upward, vertically upward, means r must be greater than mg, so the body is moving with a resultant force. What is that resultant force? F. If m is the mass and a, ma is equal to r minus mg. My point is, what is the apparent weight? That is the normal reaction. So you are inside the lift, and the lift will gives the reaction, normal reaction. The floor of the lift gives, that is the apparent weight. R is equal to, what I can write here, m of A plus G. R is equal to M of A plus G. Okay. So the effective, or you can say here, the reaction has increased. Therefore, the portion has an apparent weight greater than its has an apparent weight greater than the true weight. Apparent weight greater than true weight. Why? True weight is mg, or you can write this is equal to mg plus ma. So R is equal to mg means apparent weight equal to true weight, but here R is equal to mg plus a, so apparent weight must be greater than the true weight. So here you can say that the effective value of acceleration due to gravity, according to R, you can find out the acceleration due to gravity here is not g. The acceleration due to gravity, suppose g dash, if you put R is equal to mg dash, mass into g dash, mg dash is equal to mg plus ma. So if m cancels, g dash is equal to g plus a. So for this portion moving vertically upward, the acceleration due to gravity, the effective value of acceleration due to gravity is g plus a. G plus a, with what acceleration it goes up. Okay. Then next we will go for the fourth case. Then the lift is moving vertically downward. Fourth one. Then the lift is moving vertically downward with uniform acceleration. Here the lift is coming vertically downward. So here again do the same procedure is that if the lift is coming vertically downward, then the force, resultant force F is equal to, which one is greater? Vertically downward means mg greater than R. There are the two forces mg and R. Because of imbalance, you are getting this resultant. The lift is moving with acceleration a, right? Mg minus R. Or F equal to, if moving with an acceleration a, ma is equal to mg minus R. So R is equal to mg plus a. R is equal to m into g minus a, right? This is g minus a. R is equal to m g minus a. This is the apparent weight. Or I can write R is equal to mg true weight minus ma. So which one is greater here? Obviously mg is greater because mg minus ma is equal to R. So I can write true weight is greater than apparent weight. True weight greater than apparent weight. Clear? And the effective value of g also you can find. G dash is equal to g minus a. G minus a. Clear? So that is equal to apparent true weight and the apparent weight. So what he will feel? Apparent weight is less, means he feel that its weight, his weight is decreasing. Then when the lift is moving vertically downward with an acceleration equal to g. Fifth case. Then already using this formula only, vertically downward, but instead of acceleration, this uniform acceleration, it is moving with an acceleration g. So when vertically downward, R is equal to m into g minus a, the apparent weight. And A is equal to G moving vertically downward, so R is equal to m into G minus G, so R is equal to 0. So the apparent weight is equal to 0. Apparent weight is equal to 0. Who provides this apparent weight? The floor of the lift provides the apparent weights. The floor of the lift provides the apparent weight. Also, this apparent weight means the person feel its weight. So its apparent weight is 0 means he will feel weightlessness. He will feel, the person will feel weightlessness. He feels that he has no weight, weightlessness. right? Then the lift is moving vertically downward. Okay, so now vertically downward with an acceleration A greater than G. Sixth one, when the lift is moving vertically downward with an acceleration which is greater than the acceleration due to gravity. But other two cases, here it is up to equal. Now, what you will get here? If acceleration is greater than G, A is greater than G means G minus A. Generally, we are on the surface of Earth near the surface of 9.8 is more than that, 10 or 11 like that. So, you will get a what? Negative. R is negative. So, R is negative means this R is acting like that, means R is negative means like this. So, this is the case like the person will feel that this R negative means the person will hit the ceiling. Means he will feel in this case, if negative apparent wave, in this case the person will rise from the floor of the lift, and goes or hit to the ceiling and hit to the or against the and crash against the ceiling of the lift. He will crash against the ceiling of the lift because R is negative. Okay, so these are the different cases for a person inside the lift. Okay, students, so go through this video, and I already told that this is like a numerical type or a application type of Newton's law, and try to understand the normal reaction. And when we are go for next videos, we will discuss again more detail about this normal reaction. But for this, we all of you got the idea about normal reaction. Okay, students, thank you.